Okay, hi. This is uh, Romeo Tolentino of NU Manila, and I'm going to discuss the first lesson of differential equations. Alright, let's start with lesson 1, definitions and terminology. Okay, let us define a differential equation. Now, a differential equation, or rather an equation containing the derivatives of one or more dependent variables with respect to one or more independent variables is said to be a differential equation. So here we will start to call that DE. Now, basically a DE is an equation that involves derivatives. That's a simple, okay, that's a simple what? That's a simple definition. Next is, let us distinguish between an ordinary equation and a differential equation, the difference. Okay, now equation has a constant for a solution while a DE has a function for a solution. Now a specific example is, okay, let's have this equation x plus 2 is 1. By inspection, the solution of this is x is negative 1. While this equation, this is now already a differential equation because of the existence of a derivative there. As a solution of y is x squared plus c. Notice that this is an equation of a family of parabolas. Okay. Now let's see if this will satisfy this equation. No? So let's get dy dx. So what is your dy dx? Your dy dx there is what? Is actually equal to 2x. The derivative of what? The derivative of c is 0, and if you plug it there you will have 2x minus 2x is 0. Okay, so what's now the distinction? The distinction is that, again, for an equation, it is the solution is a constant. For a differential equation, the solution is a function. Okay, next is, okay, let us classify differential equation by type. Now, an ordinary differential equation, ODE, is a differential containing only ordinary derivatives of one or more functions with respect to a single independent variable. So there is just one single independent variable here. So actually in this course we will just only study ODE only. Okay, so the first example is an ODE. Okay, because the independent variable here is only x. Okay, here the next equation is again an ODE because what? Because there is only one independent variable, it is x. Okay, the parenthesis there is a function of x. And the next DE is also an ODE because the independent variable is t. Okay, of course the dependent here is y and x. Now, when you call a PDE, what is now a PDE, or a partial differential equation? It's an equation involving only partial derivatives of one or more functions of two or more independent variables. Now observe how this symbol is used as second partial derivative of u with respect to x and second partial derivative of u with respect to y. The independent variables here are two. There are x and y. Here also x and y. Now we will not study PDE in this course. Okay, we'll just be concentrating on the solution of an ordinary DE or ODE. Okay. Now let us classify now DE by order. Okay, so let us define first what is an order. The order of a differential equation is the order of the highest derivative in an equation. And the degree of a differential equation is the algebraic degree or exponent of the highest order derivative after clearing off all the fractional exponents in the derivatives. Okay. Now look at these examples. Now this is second order. Why is it second order? Because the highest derivative there is d squared y dx squared, or y has been differentiated maximum twice. And why is it third degree? Okay, you may mistook this to be what will be fifth degree, but it should be third degree because the exponent of the highest derivative is third degree. Now here this is a PDE. Okay, it's fourth order. Look at this, fourth order, and first degree. The power of what, or the exponent of this is 1. Now this is second order and fifth degree. Why second order? Because this is y double prime. And why this is fifth degree? Okay, you have to raise this to what? Raise this to the second power. Okay, second power, to remove that exponent there. So that means this will just be y double prime raised to the what? Raised to the 5 is equal to what? Is equal to x squared y squared, and therefore this is what? This is second order and fifth degree. This is the basis, y double prime, and that 5 there, fifth degree. Now let us now classify, okay, differential equation by linearity. Now let us define what is the meaning of linearity. An nth order ordinary differential equation is said to be linear in the variable y if f is linear in y prime, and so on. This means that an nth order ODE is linear when it follows the form. Now let us analyze this form. Notice that, okay, the coefficients here, a and x, and so on, a and 1, these are all coefficients of x. Okay, and then these are all what? First degree, dn y, dxn, dn minus y, dxn. This is nth order, first degree, n minus 1. This is 1 less than the order of this, and so on. Okay, now, okay, there are two indications of linearity. Okay, this is the first one. And the second one, the dependent variable y and all its derivatives, y prime, y double prime, 1 y to the n, are of the first degree. Meaning, look at this. These are all what? The power of dn1, dxn, and so on. These are all first degree. And then the next is the coefficients. These are the coefficients a0, a1, an of y prime, y double prime, yn, depend at most on the independent variable x. Okay, or it could be constants. Okay, let's have an example. Y double prime minus 2y prime plus y is 0 is linear. Why? These are all what? These are all first degree, and the coefficients are just constants, and the right side is also a constant, 0. So this is linear. What about this? Why is it linear? So look, this is x cubed, 2x. All of these are what? Are functions of x. And the second derivative and the first derivative has, okay, exponent 1 or first degree, and therefore it is linear. Now this is non-linear. Why? Because of the presence of 1 plus y there. It is a function of y and not a function of x, so it will make it non-linear. Now what about this one? This y squared, okay, this should have been what? This should be a function of x, since this is y squared, and then the order, this is second degree. This is second degree, and at the same time, this is not what? This is not a function of x, so this will make this DE non-linear. Okay, next is we have solution of a DE. A solution of a DE is a relation connecting independent and dependent variables which satisfy the differential equation. Well, at the start of the discussion, I have explained already to you a solution of a DE because I differentiated between what? Between a solution of a DE and a solution of a constant, and a solution which is a constant for an ordinary equation. So again, this is defined here, a solution of a DE. Okay, okay, we're now expecting what? We're now expecting function. So, okay, a general solution is a solution containing arbitrary constants equal to the order of the DE, and a particular solution is a solution obtained from the general solution by giving particular values to the arbitrary constants. Now let's have some example. Look at this, look at this differential equation, y double minus x. This is what? This is second order and first degree DE. Okay, the solution is y is x cubed over 6 plus c1x plus c2. Okay, why is this so? Okay, now look, if we integrate x, okay, because this is second derivative, we will have to undo the derivative twice, so we'll have to integrate. The integral of, okay, x dx is x squared over 2 plus c1. c1 here is an arbitrary constant. Next is, if you integrate it again, you get y, which is what? X squared over 2 plus c1x. That will be x cubed over 6 plus c1 x squared over 2 plus c2. Notice that this c1 and c2 are arbitrary here, and if this is second order, expect that there will be two arbitrary constants here. Now look, this is the solution actually is a function, okay, or as what is defined here, this is connecting independent and dependent variables. Okay, so the dependent variable here is y, and it connects with x, and this is actually representing a function. Now this is a general solution because what? Because you have c1 and c2 here as arbitrary constants. Okay, how many arbitrary constants do we have? Actually, there are two, and of course, this is what? This is second order differential equation. Now, any solution that can be obtained from the general solution by giving particular values to C1 and C2 is called a particular solution. So that means if we what? If we give values for C1 and C2 which will depend upon the condition of the problem, okay, that will give you now a particular solution. And this general solution, another term for that is a primitive, okay, or a primitive or a general solution. Now there is a theorem: the general solution or primitive of a differential equation of order n always contains exactly n essential arbitrary constants. Now here I've been explaining there are two arbitrary constants, okay, and our differential equation is second order. What do you call this again? This is called what? This is called a primitive or a general solution. Okay. Now the solution of the DE, okay, this is x dy plus y dx is 0, is xy is c. This xy c is actually a family of hyperbolas. Now let's visualize that. So actually, alright, if this is your y and x, So this will represent a family of hyperbolas like that. Okay, if c is negative, it will be like that, or like that, or like that. Okay, so of course it will always what? It will always uh, pass, okay, through the origin. Now, no, we get the derivatives of both x and y here. So, okay, here, this is x, y is c. Okay, get the derivative of a product. Okay, you get what? X times the derivative of y plus y times the derivative of x is 0. You see, this is the differential equation that arises from x, y, c. Again, this is a family of equilateral hyperbolas. Next, if the curve passes through 1, 2, then it's possible for us to determine a particular solution. Again, we call this what? General solution or primitive. Then it's possible for us to determine the value of c. Substitute x is 1 and y is 2, then 1 times 2 is c, or c is 2. That means if at this particular point, let's say here, so this is 1, 2, 1, 2, okay, we will have what? We will have specific, okay, just one parabola, just one hyperbola that passes through 1 to there. This is one, or this will represent one curve of the family of hyperbolas. Now here, we now have a particular solution which is xy equals 2 because we have determined already the value of c. Observe that this is just a first order differential equation, so expect that we have only what? We have only one arbitrary constant. Now, show that y is sine x and y is cosine x are solutions of y double prime plus y is 0. Well, all we have to do is to get the first and second derivative and then substitute it here. So for y is sine x, okay, what's the first derivative? First derivative is cosine x and second derivative is negative sine x. We will have to plug it there. Okay, so what do you get? Y double prime is here, negative sine x is there, and ry is here, sine x. And if you add, the value turns out to be 0. Okay, therefore, by the definition of a solution of the DE, this is what? This is a solution, or y sine x is a solution. What about y is cosine x? For y is cosine x, the first derivative is negative sine x and the second derivative is negative cosine x. Observe that if I add these two, okay, alright, this will what? And substituted it here, this will satisfy this one because when you add it there, the value is 0. You conclude then that y is cosine x is a solution. So both sine x and cosine x represent solution of y double prime plus y is 0. Now it means now that, okay, y is sine x and y is cosine x are solutions of the DE y double prime plus y is 0. Now when you say collections of all solutions, okay, this will now be c1 sine x plus c2 cosine x. This will be now a primitive or a general solution of the differential equation y double prime plus y is 0. Next. Now let us distinguish now between initial and boundary value problems. Now in the past, right, in the previous example, we have the general solution of y double prime plus y 0 is y is c1 plus c2 sine x. Now, it's possible for us now to determine particular solution. Now, the solution, okay, let us distinguish now between initial condition and boundary conditions. Now, in an initial condition, the solution of a DE is required to satisfy additional conditions at the same value of the independent variable. Now notice that, okay, there is only one value of independent variable, and then you have this dependent variable that y is 1 and y prime is 0. So here, if x is 0, y is 1, and y prime is 0, it's possible for us to determine C1 and C2. So we have here, this is our primitive or general solution. Plug what? 1 equals C1 cosine 0 plus C2 sine 0. Of course, this is what? This is 0, and therefore this is 1, and therefore C1 is 1. And get the first derivative, negative C1 sine x plus C2 cosine x, and plug 0 is equal to negative C1, okay, sine 0 plus C2 cosine 0. Of course, this is 0, and this is 1, so therefore C2 is 0. Now C2 is 0 and C1 is alright, Z1 is 1 and C2 is 0. Then what will be our solution here? C1 is 1 and C2 is 0. The solution will just be what? Y is cosine x. Now the difference between initial condition and boundary condition is that in a boundary condition, okay, there are different values of independent variables. So in here, okay, you see that the condition is when x is 0, y is 1, and when x is pi, y is negative 1. You see that there are two different values of independent variables in order for us to determine C1 and C2. So just plug it there. Okay, 1 equals C1 cosine 0 plus C2 sine 0. This is 0. This is 1. Therefore, C1 is 1. And get the first derivative, negative C1 sine x, again here, plus C2 cosine x, and plug what? Plug when x is pi, y is negative 1. So this is negative 1 is negative C1 sine pi plus C2 cosine pi. Alright, observe that this is what? This is 0, and cosine pi is what? Negative 1. So what is the value of C2? C2 is 1. Okay, C2 is 1 and C1 is 1. Then we have a particular solution. We know already the values of C1 and C2, that is cosine x and sine x. So this gives you a particular solution. Okay, let's summarize again. When you talk of initial condition, okay, what can we say about the values of the independent variable? They are the same. While in boundary conditions, the values of the independent variable are different. Okay. Next is we do some verification of the given functions. Okay. Verify that the given functions are solutions of what? Of the given DE. What we have to do here is only what? In this problem, what we have to do is just substitute this here. If it satisfies, it is a solution. Okay, otherwise it is not. So here is the given, and then we're just going to plug it there. Okay, alright. Get the derivative of y and substitute to the given d. Your y is c1 sine 2x plus c2 cosine 2x. First derivative is 2c1 cosine 2x minus 2c2 sine 2x. Remember that the derivative of 2x there is 2. And y double prime is negative 4c1 sine 2x minus 4c2 cosine 2x. And then plug it in this y double prime plus 4y 0, and see it's gonna be, it will satisfy 0 here. Okay, this is negative 4c1 sine 2x here minus 4c2 cosine 2x, okay, plus 4c1 sine 2x plus c2 cosine 2x. If you notice that, okay, the left is this and this, okay, negates each other. Okay, so negative 4, this will cancel out, negative 4 and then negative 4 and negative 4 cos c2 cosine 2x, and 4c2 cosine 2x is 0. Then we say that this, this is a primitive or a solution. In fact, it's called the general solution of y double prime plus 4y 0. Okay, next is, let's verify if y is 1 over 16x to the fourth is a solution of this. There's no arbitrary constant, so this is actually, okay, so this is actually a solution, no? Okay, let's see if it's a solution, if it satisfies this differential equation. So get the derivative of y. Okay, the first derivative is 1 over 16x to the 4th. Okay, that's the y. The first derivative is, this is just y, 1 over 16x to the 4th. And the first derivative is 1/4. That is 1 over 16 times 4. That's 1/4. And then, okay, subtract 4 by 1. It's 1/4 x cubed. And then let us substitute. I'm going to substitute here. So on dy dx is xy raised to 1. Okay, let us rewrite this as your dy dx is the same as y prime. Okay, let's just rewrite that as y prime minus xy to 1/2 is 0. Okay, and then substitute that what? Substitute that 1/4 x cubed there. Okay, so 1/4 x cubed minus x times substitute y there. You have what? 1 over 16x to the 4th 1/2. That's 1/4 x cubed minus this is square root of 1 over 16. That's 1/4 square root of x to the 4th is x squared. And then 1/4 x cubed. This will transform. This is also 1/4 x cubed. And the result is 0. It means that y is 1 over 16x to the 4th is a solution of this DE. Next is, okay, let's see if this will satisfy this differential equation. Okay, we need the first and the second derivative. Okay, so get the derivative. Okay, the first derivative is t to t. Use the derivative of a product. The first derivative is, okay, no, the function is t to t. The first derivative is, okay, product t to t plus e to the t times the derivative of t, that is 1. And the next derivative is, of course, it will be repeated, t e to the t plus another e to the t times t plus another e to the t times t. This will combine, that's 2e to the t. Okay, and then what to do is plug it there. Plug it there, okay, and there, and there. Plug it there and verify if it will give you 0. So, okay, that is te to the t plus 2e to the t and then minus 2 times te to the t plus e to the t. This is the first derivative plus the original function is t to the t. It simplifies to te to the t plus 2e to the t minus 2te to the t. This is minus 2e to the t plus te to the t. Right, this is t to the t. This will cancel out here and this will cancel out there. So the result is 0. That means what? T to the t is a solution of, of is a solution of okay, the differential equation.